it's time to start. Good to see you everybody here, and thanks for being here. It's great honor to introduce today's speaker, Professor William Shih from Harvard. He got PSPA, maybe, since 1994 at Harvard, and then he completed his PhD at Stanford 2000. And then, as far as I remember, he spent his postdoc career about 4 years. And then 2005, he became independent at the Harvard. As you might recognize, he is the pioneer of the DNA nanotechnology field. Particularly, he made a lot of contribution to diversifying the accessible DNA nanostructure motif. Particularly, he expanded previously 2D limited DNA origami to the three-dimensional counterpart and make them more mechanical robust, and which in turn allows to have more diversified applications. So that was published in 2009 in Nature and Science. Also, he proved that the rigid duplex can be bended with controlled curvature. And 2 or 3 years ago, he made another breakthrough. This called critical polymerization. Through that, the accessible size of DNA nanostructure can be greatly expanded. Previously, the individual DNA origami can have about the 100 nanometer in the upper limit in terms of size, but nowadays it can be extended to the few micrometers through his one method called critical polymerization. Maybe he will share about that progress. Yeah, it's time to give you the William. So please join me welcoming him with big hand, please.
Great. Well, thanks a lot to Professor Sung Lee for hosting me and introducing me. It's really wonderful to be back in Korea. And thanks to friends in Busan, Professor Min-Suk Kwak, for joining in. It's really my pleasure to share with you this new mode of self-assembly that we've been exploring that we call crisscross polymerization. Many of you are familiar with DNA origami, and maybe I can start with that and the story of how we were able to do something useful in the therapeutic arena with DNA origami or to make a cancer vaccine. And then the rest of my presentation will be about this crisscross polymerization method. So DNA origami, many of you have probably seen this movie before. You start with the long single-stranded genome, typically of the 7,000 base genome of the M13 bacteriophage. We know what that sequence is, and based on that known sequence, we chemically synthesize hundreds of DNA staple strands that are 20 to 60 bases long, that are programmed to pair by Watson-Crick base pairing to pinch together different sections of that long scaffold, such that collectively you knit that long scaffold into a set of parallel loops. And so, for example, we might have here a yellow staple strand that pairs 1.5 turns on the bottom part, and it jumps through a different part, and it draws that together again through base pairing. And that in this way, one's able to create various 2-dimensional and 3-dimensional shapes. So this is the disc with 3 holes from Paul Rodemund. He invented DNA origami in 2006. And maybe I can say the thing about DNA origami that seems the most magical to me is that for every molecule of scaffold that you add to a solution, you get exactly one DNA origami out. It's being bathed in a rich broth of excess staple strands, and it's very, very efficient that you form these structures. If you add 0 copies of the scaffold, you get nothing. And so you could imagine how a method like this might be useful for detection if you could trigger self-assembly of a large particle just by the presence of that analyte. And I'll return to that thought in a bit. So one of the useful applications that we were inspired to pursue was to make a DNA origami-based cancer vaccine. And this is work that was initiated in collaboration with a visiting scientist from KIST, Dr. Juhi Ryu, who helped to recruit the lead scientist on this, Dr. Claire Young Zhang. Her name is hiding behind this. Well, it's hiding behind the thing that says talking, but Dr. Zhang led this project, and we've had other collaborators like Professor Ik-Jung Kwan at KIST. And here we were inspired from the amazing breakthroughs in cancer immunotherapy, where you have these checkpoint blockade inhibitors that basically relieve the inhibition of T cells that are needed to kill off the tumor cells. And I'm not going to go into great detail about this project. I just want to give you a flavor of what's involved. Anyways, one of the issues with these amazing, miraculous checkpoint blockade drugs is that they only work for maybe 10 to 20% of the patients, and that's only for certain cancers. And therefore, there's a lot of motivation for trying to increase the applicability of these vaccines so that of these checkpoint blockade inhibitors so that they'll work on a much larger fraction of the population. And so that's where the motivation to come up with a vaccine is, that maybe if we can deliver a vaccine to people who don't respond to this antibody drug, that can reawaken the giant of their immune systems and then allow them to enjoy the benefits of the drug. And based on some hints from the literature, we thought, well, maybe if we can decorate a DNA origami particle with a high density of an immune stimulating molecule known as a CpG oligonucleotide with defined spacing, maybe that would be the trick to help wake up the immune system to make them more responsive to killing off things like tumor cells. And the actual reasons for why that might be true are still kind of murky, but sometimes in science it works like that. You just have this idea, you're not quite sure why it'll work, but you explore it anyways. And although that might seem like a weird motivation, we found that in fact, the exact spacing of these ligands on the particles did make a big difference. So here what we did was we fixed the number of ligands at 18. These 21 were CpG oligonucleotides coming out of one face of this origami that itself is about 25 nanometers per dimension. We tried different spacings, and what we found is that a spacing of about 3.5 nanometers was much more effective than the other spacings at triggering this polarization of the immune system that made it more susceptible to attacking the cancers. So we thought that was quite remarkable. So this is just an example of the kind of experiments that we do. So in this case, we inject about 500,000 of these melanoma tumor cells into one part of the mouse body. And ordinarily, if you don't do anything else, the mice will die within short order. And then we test whether or not an experimental vaccine can now delay that death by the introduced tumor, or maybe even prevent disease altogether. And so in this specific example, we're giving our DNA origami vaccine to the mouse days 3, 7, and 14 after we introduce those tumor cells. And what we see here is a plot of survival of the mice on the y-axis and then time on the x-axis. And what we can see is, I'll just point out that the green line where the survival is longer, that's with that 3.5 nanometer spacing. And there's a ton more work in our paper. I encourage you to check out. It was recently published in Nature Nanotechnology if you'd like to learn more about this. And now we've started just full disclosure, we've started a company around this to try to commercialize that we call Dory Nano. So myself and Claire and also Drs. Ryu and Dr. Kwan are all co-founders. Okay, so this is a case where we found that the precise nanoscale presentation of these ligands to a certain kind of immune cell, a dendritic cell, made a big difference in how that immune cell responded in a therapeutically interesting fashion. And then that led us to think about the question, well, all right, we were able to self-assemble something the size of a small virus, about 25 nanometers. What's to stop us from self-assembling something of that same kind of control, but now the size of a biological cell? Why can't we just self-assemble something the size of an E. coli bacterium? And for, I think most of you recognize, just because I can utter those syllables, it's a kind of ridiculous concept. So why would you be able to just self-assemble something of amazing complexity? It's a very difficult thing to do, but nevertheless, even though it sounds crazy, we think that this method of crisscross polymerization actually offers a path to getting there in the not too distant future. And so this is just one inspiration for why we might want to do this. On the left-hand side is a scanning electron micrograph of a dendritic cell or immune sentinel cell, false colored in cyan, and then a T cell that it's trying to instruct and activate false colored in yellow. And the important thing here is that the interface between those two cells spans multiple micrometers in dimension. And there's a specific patterning across the micrometer scale of the receptors and ligands within that interface. So if you have a central cluster of these complexes, then that's actually an inhibitory signal, versus if you had nanoscale clustered around the periphery, that can be an activating signal. So our hypothesis is that we can have a material that is micrometers in overall dimensions, but we can pattern things specifically, then we could now create a medicine that can activate T cells in the way that we want with these micrometer spatial cues. But the only problem is, up to this point, nobody had any method for generating objects with this kind of spatial control. The closest anybody had gotten was this method from Gregory Tikhonov and Lulu Chen that they published in from Caltech, that they published in Nature in 2017. And here what they did was they sequentially made 64 different origami that they could stitch together into a quilt. And they had to be extremely careful in trying to do this to get any success at all. First, what they did was they mixed together 4 origami at a time to make these tetra origamis, in each in a different test tube. And then they had it programmed so now they could take 4 of those and mix those together into a test tube to make these 16 origami structures in 4 different test tubes. And then the third step, they could mix 4 of those together to make the final 64 origami structure. And the good news is that the yields, if they were extremely careful about concentration and temperature and everything in design, they could get really good yields for the 4 origami structures, not so bad yields for the 16 origami structures, but now pretty terrible yields once they got to 64 origamis, about 2%. So this is quite striking that with the method used to build just one of these origami, you can add hundreds of staple strands together. And from the point of view of the scaffold that you're adding, the yield is close to 100%. And yet when you try to hierarchically link together these origami into a bigger structure, it seems impossible that you could have any yield at all of mixing 200 of these together. So what's the difference? Why is it working to make one origami, but not working to make a super huge structure? Maybe you could say the DNA origami, just a single one, is cheating because it has this long scaffold strand in order to organize all those staple strands together into one object. And we simply don't have access to anything proportionally large scaffold to bring together hundreds of origami. So maybe that might be a problem or excuse, but we sought to solve this problem using a different kind of mechanism. So we still wanted to be able to control the assembly of this hierarchical assembly with some kind of seed molecule, but we didn't want to force that seed molecule to be half the mass of the final assembly. We want the seed to be as small as the building blocks themselves. That so the question is, could we make the origami of origamis? Could we have origami level efficiency of assembling many origami into a much larger structure? And so this is the work that we published in Nature Nanotechnology about a year ago with lead authors Chris Wintersinger, Diominov, and Anastasia Ershova. They were all PhD students. They've all now graduated. Anastasia stayed on as a VC staff scientist. The building blocks for these are each a DNA origami. It's a 6-helix bundle DNA nanotube. It's about 450 nanometers long, and we programmed it to display glues, single-stranded glues, every 14 nanometers, 14 nanometers, at 32 positions. And what we found what works well is if each of these glues is a 7-nucleotide specific sequence or its complement. And what we do is we program any 2 of these elements that are supposed to interact. We program the complementarity so that they're only going to be complementary at one of those 32 positions, and that ideally none of the other ones. And we operate the self-assembly at a temperature where we're just making one of these glues is not enough, not nearly enough for stable attachment. So if it interacts at all, it just transiently kisses and then it falls apart. In order to form a stable structure, we thermodynamically require a much larger number of structures to coordinate together. into a structure like this. So what this represents is a top layer of vertical slats, each one different. There's, in this case, 32 of them, and then below them are 32 horizontal slats. So none of the vertical slats are touching each other, none of the horizontal slats are touching each other. They're only, horizontal slats only can interact with vertical slats and vice versa. Every vertical slat then is making a bond, specific bond to 32 different horizontal slats. And now it's a very, very stable structure because every slat is making 32 bonds. The important thing here that we're trying to enforce is that there's the structure that's thermodynamically favored, but it's never, ever going to form kinetically unless you provide some kind of seed molecule to initiate the process. It's a strictly seed-dependent process. And so how do we enforce that? We can imagine in this case, what if we did the self-assembly at a temperature where you need 16 bonds for stable attachment? This is the reversible temperature for assembly. And so we can imagine in such a situation that the critical nucleus, the point at which now the assembly can be downhill, is one in which you have 16 horizontal slats and 16 vertical slats. That's a case where now every subsequent slat addition is making at least 16 bonds. That means in order to get to the critical nucleus, starting from individual slats, you have to go through 32 very unfavorable steps. Each time you're adding a slat, you're making far fewer than 16 bonds, and that means it's energetically unfavorable. In order to get to this critical nucleus, it's basically like you're paying the entropy cost of bringing 16 of those slats into exactly the right configuration, and nothing is holding it together. So we could imagine that, well, maybe each one of these is something like 20 kT of energy to bring it into exactly the right space. And if we have to do that 16 times, then the energetic cost of reaching this critical nucleus is something like 300 kT. So that's an extraordinarily high energy barrier. You could fill the ocean with these and wait the age of the universe, and nothing will happen, even though it's thermodynamically favored. That's how vast a number we're talking about. Instead, what we can have is a process where if we now introduce a red seed, which is just one DNA origami, it's now like a little cheat code where it's using very strong non-cooperative binding to grab the first 16 special slats. So this is kind of conventional self-assembly using irreversible bonding. And then it's using that strong bonding to pay that entropy price to fix those first 16. And once you've done that, and that's now all downhill, where you can capture the subsequent slats, 16 bonds each, and you can arrive to the final structure. This is a negative state transmission electron micrograph of one of these structures. In the background, if you squint, you can see the original DNA origami, like little shadows in the background. Those are about 80 by 80 nanometers. This is a gallery of structures, and they all look pretty good. There's some missing slats. So under best conditions, we might find on average about 2 to 3% of any given slat might be missing stochastically. And we think that has to do with defects in the DNA origami, that we know certain strands are just not there. And that could potentially explain why you do get defects. But the good news is that the overall assembly works, even though there's local defects. Here's a zoom out, 6-micron scale bar, and you'd be hard-pressed to find anything that looks like an incomplete square. So the first approximation, this is like DNA origami in that it's all or nothing assembly. Either you have a seed that initiates assembly that goes to completion, or nothing happens, even though thermodynamically all the slats should be coming together to make these structures. That emboldened us to try to see if we can make bigger structures. Our next target was with something with almost 200 building blocks, which is like the complexity of a DNA origami itself. In this case, it's a plus sign. We have this paradigm where the red seed captures the first 16 slats using those strong binding interactions, and then this regular crisscross. After that, we have a bidirectional growth front, one growth front to the right, one to the left. And so if we just follow the one to the right, then you can kind of see a growth front that goes up to the right, down to the right, down to the left, et cetera, et cetera. It's like doing a logo turtle around a deterministic growth path to build the final structure. And so here's an example of the structure. It's almost a micron in dimension, over 1 gigadalton in mass. For those of you who are biologists, keep in mind each one of these DNA origamis is about twice the mass of a bacterial ribosome. So this, you could count it in bacterial ribosome equivalents. This is almost 400 bacterial ribosomes worth of mass. Here's a structure where the seed was placed on the South Pole. You have this bidirectional growth front with the two ends. Actually, because these are kind of flexible, oftentimes they'll just grow past each other, like lovers that can never meet each other. But sometimes they do meet and you form the complete structure. This one has almost 1,000 slats. The dimensions are about 2 micron by 2 micron. In this case, the seed is placed on the upper left-hand corner. You have this bidirectional growth front. And then now with 1,000 building blocks, we can start to see some limitations of this method in terms of reaching the final growth. If we take a zoom out, we can tabulate how many of these seeds actually lead to complete assembly. We can see the complete ones circled in red and an incomplete one in cyan. It's about 20 to 25% of the seeds make it all the way to the end, which if you think about it, that's pretty good. If you had a uniform fail rate that could terminate, you have these 1,000 steps, and you can actually make it all the way through those 1,000 steps 25% of the time. That corresponds to a per slat success rate of 99.85%. So not too bad. We're trying to make that even better, but I was really surprised that it worked this well, because most things that you try don't work this well. This is the biggest structure that we've made so far. It's 1,024 slats, 2 micrometer by 2 micrometer. The seed is on the North Pole. You have this bidirectional growth front. Note here, the two ends do not meet. So the two ends don't have to meet. You could design it either way. Again, keep in mind that all 1,000 slats, they're different entities, each one made in a different test tube with potentially different functionalities. And to just drive that point home, here's a movie of a seed. It captures the first 16 special slats using those strong binding. And then after that, it's the regular crisscross polymerization. We have a bidirectional growth front, one to the left, one to the right. Let's just focus on the growth front to the right. So now we're capturing 16 slats going down to the right, down to the left, down to the right, down to the left. So we make the final structure. Because each one is completely different, we could predetermine that it forms a specific pattern of ligands that are displayed. In this case, what we did is we programmed certain handle positions to display a 16-base acceptor. And then to visualize that, give contrast, we then added a DNA nanocube, which is a 10 nanometer nanostructure that has a complementary strand that only will adhere to the structure in the place where one of those handle is placed. So in that way, these the 500 top slats are cooperating to build an image. And then on the left is the design, on the right is what we see under the electron microscope. It's 2 micrometer by 2 micrometer. In this case, we're happy we got the cover of Nature Now technology. In this case, this was Photoshop to take the same structure and arrange it in this way. But we think maybe by combining with top-down lithography, it might be possible to dock these structures in this way. Or maybe this just through pure self-assembly, one could imagine maybe linking these things together as well. Stay tuned. We made 4 different structures. This is the puzzle piece. This is a DNA double helix with the Beast Institute logo. This is supposed to be the logo for the Harvard School of Engineering and Applied Sciences. All right, so for this first part of my talk, one of the questions is, well, why is it that we were able to succeed? People have been trying to hierarchically build DNA origami into these big complicated structures since it started in 2006. And we think of our method as a big leap forward. So what is it about our method that really helped us to succeed where all previous methods have not succeeded? And to be honest with you, I'm not quite sure. I feel like other methods should work, but somehow they just haven't. But maybe if you have some inbuilt advantages like we do, it could help your case. And so some of the things that help are we think this absolute seed dependence, now you don't have to worry about the assembly starting from different parts, and then you make a bunch of unwanted side products that all look different. I think the fact that we have very rapid and robust error-free growth, that we specify attachment with these 16 binding sites, each one is weak. This is a combinatorial code that we can make very orthogonal. I think it's just a very, very robust way to make things fit together. So I suspect there'll be other methods developed to make these hierarchical structures, but I don't know, maybe we won't see them for a while. In the meantime, we'll be continuing to improve this method. So this is our paradigm of a nanobeam that gives rise to a microstructure. Some of you might be wondering, where are we taking this method? So some of the next directions are that we want to make it easier to use for everybody, or for ourselves, but then for everybody else in the community. One of the things this requires a huge number of pipetting interactions. I think 30,000 pipetting interactions to make one of these structures. And you really need a pipetting robot to do that. But we're developing methods where an outside user doesn't need a pipetting robot. They just need to do one pipetting step for every functionality that they wanted to build in. So that would make things a lot easier if you don't have access to a pipetting robot. And then we've been working with growth on magnetic bead supports that could, we think, make things a lot more robust and faster. We're interested in using those advances to build structures that are more complicated. So one ideal is, well, could we extend from 1,000 slats to 4,000 slats? We make a structure that's 4 micrometer by 4 micrometer. That's the first step. But then we're interested in other kinds of increases in complexity. Could we take this structure and then grow it layer by layer to make a solid 3-dimensional structure? Or could we imagine building in creases into the object and folding the object up along those creases to make hollow 3-dimensional objects? I think that could have some interesting abilities. And then finally, could we program more exotic behaviors than rather just growth, but could we have things like growth with scission? We could have something that grows and divides, maybe with information processing, such that you could recapitulate Darwinian evolution with an isothermal system without any bond breaking or making. So with the remaining time in my talk, I'd like to discuss a parallel effort in our group to implement this crisscross self-assembly with what I think of as a very different building block, which is just single-stranded DNA slats. Now, it's also DNA like the DNA origami, but to me, it's very, very different. In this case, we envision this in this example, it's a, let's say, 66mer that I think of as 12 different 6 or 5 nucleotide binding sites. So those are the individual segments. And as with before, we have this 90-degree association between vertical slats and horizontal slats, where the individual interaction is very, very weak. And so it's transient, it kisses and then it falls apart. But the final stable structure involves coordination of many different slats together. Again, we have this idea of a critical nucleus, where in this example, we need to make 6 bonds for stable attachment. And in this example, then the critical nucleus would have 6 horizontal slats and 6 vertical slats. And that, again, generates a sizable kinetic barrier against nucleation so that we can make everything completely seed dependent. And why would we want to do this instead of using DNA origami building blocks? Well, one of the applications of this is we could do signal amplification for, let's say, diagnostic detection. And in that case, we want the amplification to happen as quickly as possible. And to make a reaction happen as quickly as possible, you want to have a very high concentration of the building blocks. And for that, it's ideal that your building blocks will be as small as possible. So they'll be as inexpensive as possible, but you can also just pack them in at much higher concentration. So that's the main motivation for when you'd want to use these very small building blocks. Versus if we want to just build something really big, then I would argue using the big DNA origami building blocks can have advantages. In this case, we use a DNA origami as the seed, because you can notice that if you fold a DNA origami, then if you leave some of the single-stranded ends free, in this example, they kind of look like the end of a crisscross ribbon. You have these horizontally displayed strands that are entropically fixed in just the right place for crisscross the self-assembly. So you're using those staple strand interactions to pay the entropy to bring those single-stranded elements into high local concentration with just the right arrangement. After capturing the first 6 helper Y slats, then we can have the regular crisscross assembly. And then in this way, we can make these repeating ribbons where in this example, there's 12 X and 12 Y slats. So there's a set of 24 slats that repeat in this object. And so here's a transmission electron micrograph of the seed, and then the growth. The individual slots are too small to resolve by this negative stain transmission electron microscopy, but we can see the net overall structure forming of this ribbon. So it's kind of a little bit analogous to something like actin polymerization or microtubule polymerization, where you have these relatively small molecular building blocks that come together to make this much bigger object in a seed-dependent fashion. So for the purpose of diagnostics, it turns out that any linear growth through this kind of addition of molecules is going to be too slow for, let's say, single molecule detection. If you wanted to detect a single analytes and then have that lead to making enough structures that you could see with your naked eye, it would just take way too long to grow in a linear fashion. So you'd want some kind of nonlinear growth to do that. And the best way would be exponential growth, where you're continuously growing, dividing, growing, dividing. So the question is, we came up with this, how do we actually program these ribbons to grow, to divide and grow, divide and grow? How do we cut them in an isothermal reaction? So we came up with the idea of doing an analogy of toehold mediated strand displacement. In this case, you could think of that as an invading strand is separating a black strand and a blue strand by first engaging a toehold and then doing branch migration until you kick off the other strand. So in that way, these 2 strands have been separated. And we can take this analogy that I just showed you on the top that many of us are familiar with, and we could try to translate that to a crisscross structure that's now in the middle. So in this case, what we're saying is that we could displace that top blue strand from the crisscross structure with the invading long green strand. Now, one of the things that's different is that the toehold is actually composed of many different fingers. So it's like we have a virtual strand that's composed of little fingers contributed by lots of different strands. But otherwise, this process, if you squint, the process of toehold mediated strand displacement looks kind of similar comparing the top and the middle. And hopefully that sort of makes sense. All right, so the next step is in this thought experiment, what if we imagined not just one invading strand, but a series of, in this case, 6 invading strands that collectively are all engaging some kind of toehold and they're displacing strands, then we could see that the collective action of these 6 displacing strands that all go to completion, what happens is you end up severing that little right-hand portion of that structure away. So we've actually cut this DNA, this crisscross structure, into 2 pieces by the coordinated strand invasion and displacement by a little small army of displacing strands. And so that's really the key here, is that by coordinated action of many strand displacement interactions, we can actually cut these things. And so here what we did is we designed a growth motif where we introduced these single-stranded toeholds that appear at regular intervals every time we grow a repeat. And those can serve as the recruitment spots where we could bring in those invading strands. They could attach to those toeholds and do strand displacement. In this example, we have 6 on the left and then 5 on the right. And the coordinated action of those 11 strands acting together, all displacing together, leads to a scission of this structure. So I'm gonna play the movie a couple times so you can see it. So here we have 6 on the left, 5 on the right, and then they're doing strand displacement. And eventually, if that goes to completion, you end up actually cutting the structure into 2. So what happened is those invading strands displaced these now single-stranded ends that are free. I'll just play it one more time for fun. So you have invasion, strand displacement, and then cutting. So it makes a cute movie, but does it actually work? And the amazing thing is, yes, it actually works, which we're very pleased to see. So I'm just going to show you this little gel evidence here that this is a gel that's comparing linear growth where you see very little accumulation of the intercalating dye into structures because there's just not that much growth. But then if we introduce this cutting motif, then you get this accumulation, vastly more accumulation of stain into structures, which would only be possible if you had far faster growth than linear growth. And we have other evidence too, but because of time, I'm not going to go into that. More recently, we had a paper from Jie Dong and colleagues looking at another kind of nonlinear growth where we tried to make these branching structures. So in this case, we have a ribbon that's growing up and to the right, but then we also have a branch point to the left. That's happening in every case. And then the branch point to the left allows for growing of a branch off the main trunk that grows down into the left. And the branch that grows down to the left is using the exact same sequences that are growing up and to the right. And so in this example, that now creates something that's a hyperbranching growth. And we're able to make these structures. If you do hyperbranching, you rapidly run out of space. You just make these very dense particles where you have early exponential growth, but then you kind of fall off at cubic growth just because you run out of space. It's still growth, it's just not exponential at that point. We make these structures that, in this example, grow at the rate of 1 micrometer increase in diameter per hour. And one of the surprising things about this is we actually ended up depleting all the slats from the reaction volume within maybe a dozen hours or so, which if you do the math should be impossible with just cubic growth of these particles. And so what we realized what must be happening is that these particles are not just growing cubically, but they're also, at some point, they're shedding little children off. So it's actually also undergoing exponential growth through some mechanism that we don't understand. Like maybe just through physical force, pressure, it just ejects little children. And so that's interesting. And one of the remarkable things here is that we were able, because it's growing exponentially and it consumes all the slats, we're able to prove that you could imagine using this to detect single molecules. You can have a single molecule seed that then depletes all the slats in the solution within a dozen hours or so, down to a sensitivity of down to less than one copy per microliter of solution, which is pretty sensitive. So I'm going to bring that to the conclusion of my talk, which is that what we've done here is explored what we think is a new motif for a programmable self-assembly, where it's a kind of tiling. You have these tiles that come together, but because we're using this crisscross cooperativity, we have coordinated recruitment of the building blocks, that creates a regime where it has absolute seed dependence. So no seed, nothing happens, even though thermodynamically it's favored. And what we've found is that if we start with these big building blocks that are themselves origami that form this kind of porous mesh, that seems ideal for making relatively big structures, let's say on the micrometer length scale. If we want to eventually build something the size of a cell, we think we can get there with origami sized building blocks. But if your goal is, instead of doing that, you're trying to build structures, but not for the person building structures, you're just trying to build things so you can see them for amplification, then using single-stranded building blocks is preferred because you can use those at very high concentration. And then if you could also implement things like exponential growth, then you can get pretty fast amplification, which can be useful for detecting disease. So I like to think of kind of keywords of a crisscross architecture. It allows us to really tame this wild beast of nucleation that allows us to have an approximation of all or nothing growth of microstructures and very low background exponential signal amplification. So I tried to acknowledge the wonderful folks in the group that did the work with each story. I'd like to thank the following sources for financial support, and thank you for your attention. Happy to take any questions now.
Comment? How consumers like crisscross ideas.
Yeah, it's kind of a mind bender. So if you look at this structure here, if you look closely at it, there's an asymmetry between the horizontal slats and the vertical slats. So the horizontal slats look like regular DNA strands. They're just following this right-handed helical path, like they would in a double helix. And it's the vertical slats that are doing something kind of funny. So what they're doing is you have this horizontal slat that's acting fine. You have the vertical slat that comes in, it just base pairs by half a turn. And instead of doing the normal thing of continuing on, every half turn it's switching partners. Crossover, half turn, crossover, half turn, crossover, half turn. So this concept of crossing over at every possible position has been well known in DNA nanotechnology since its conception in the 1980s. It's just that nobody had actually demonstrated that this kind of thing is stable. So we just took the leap of faith that, well, what if it is stable? Then this is the perfect architecture for us to do this crisscross. And then we tried, and then we're just lucky that, oh, it actually is stable and can support this kind of growth.
Comment? So the question is that when you build these structures from the self-assembly, how do you analyze the mechanisms for driving the self-assembly and the finding energy between the base pairs and combinations?
Great, thank you. So just kind of on a larger scale, we have a toy model that describes how the system should behave thermodynamically using a bunch of simplistic assumptions. And one of the things that immediately comes out is that there should be some kind of critical temperature at which, if you go above that temperature, then not only will you stop growing, then the structure will start shrinking. And so that's one of the things that we can look for. We can analyze each of these systems and say, at what point, at what temperature is the structure stop growing, and then actually we can get things to shrink. And for the single-stranded structures that I showed, that temperature for these 12-segment structures is, and the magnesium concentrations we use is something on the order of maybe 54 degrees Celsius or so. We can also make structures with even longer slats, and then that will proportionally increase that temperature, that reversible temperature. But then there's kind of very rich analysis of the kinetic behavior beyond that we care a lot about, in terms of how do we get the fastest growth, how do we get the most uniform growth. And that has turned out to be kind of it's unveiled a very, very complicated behavior that we don't fully understand. So if we take this motif and then we just stick a bunch of different random sequences, we make different versions of it with different random sequences, each one will behave differently in terms of how fast it'll grow. And we think that there's a lot of kinetic traps that happen that we don't understand, and we'd like to get rid of them. But we're kind of in a state of ignorance of how to predict them. And one dream is that we could, if we had enough budget, we could just order enough strands to test tens of thousands of different variants, and then use machine learning in order to extract out the important features. And then maybe by analyzing that, we'd be able to figure out what the physics is. So I can just imagine, like, maybe it's some kind of, the kinetic trap involves some kind of structure where you have all these fingers, and then the fingers kind of get tangled in a specific way. And if we just had more data, then maybe we could figure out what are the patterns that tend to get tangled. And then we could if we knew that, then we could figure out, okay, how could we design the sequences to try to avoid that kinetic trap? But just so far, we haven't been able to figure it out. So I think it can get very, very complicated to fully understand the system. But in terms of the basic behavior, it seems to be behaving kind of like what we expect. I don't know if that addresses your question.
If you analyze the structures, the septum structure by TM, for example, you will see the matrix of the strands forming like some define the structures, and then is it possible to calculate the number of the bonds involved in creating those structures?
Yeah, that's an interesting question. For the single-stranded slats, the negative stain doesn't give us high enough resolution to see like if certain bonds were being missed. So I feel like we can't really answer that on a detailed question. Maybe if we could do cryo-EM, but that would be a lot of work. We can get to higher resolution. So that's an interesting question that we haven't really resolved yet. And oftentimes when we have that experimental difficulty, we just plunge ahead with a kind of veil of ignorance. So we just say, well, what if we just change the sequence or change the temperature or change the buffer and then see how that affects the bulk behavior? But then we don't look at specific defects. For the crisscross origami, the structures are big enough. Now we can resolve each individual slat. And so we can see things like there's missing slats. And so that tells us a bit more about, well, if the slat is not there, then definitely there's no bonds anywhere where that slat should be. So it gives us a little bit more flavor about some of those missing bonds. And what causes missing bonds, we think that's actually microscopic defects in the staple strands. Like the staple strand is just not there, or maybe there's some damage to the ends. So those are some of the games that we could play. But it's a really fascinating playground, but also challenging to really understand it fully.
So are they mainly kinetically trapped, meaning that the structure is stable for almost permanent time, like that? Or is it metastable, or sometimes you get thermodynamic favor?
Yeah, thank you. So our understanding from our toy model is that the critical nucleus for forming the structure when we don't want it to form is metastable. But then if we have a high enough temperature, then it basically never happens. But once you pass the critical nucleus, or more importantly, if you provide a seed, then everything after you provide the seed is now thermodynamically favored under the growth conditions, unless we go above the reversible temperature, or we change the salt or do something to destabilize it, and then we can get it to shrink. But the structures, we've had structures that we've kept for several months, and they're indistinguishable. And we know the chemical properties of DNA, that as long as you keep it at not too high a temperature, not too low a pH, it's quite chemically stable. I mean, the extreme would be, how old does DNA have to be that you extract it from fossils and you can no longer sequence it? And it's something like 1 million years. So DNA can be pretty stable as long as you don't abuse it. You keep it happy.
They also stable in the body.
Yeah, that's a great question. If you try to put these things in the body, one of the problems is that all the structures that I described, they have a requirement for divalent cations for stabilization. And physiological fluids do not have enough divalent cations. So our structures will just fly apart in physiological conditions. But what we found is we can get around that for biological applications by first pre-coating the object with a cationic polymer. So our favorite is pegylated oligolysines. It has 10 lysines, so plus 10 charge. And then it just electrostatically sticks to the structure. And then now you can get rid of the magnesium, but the oligolysine will hold it together. And then it'll survive indefinitely under physiological buffering conditions and salt. But you also have things like nucleases that will chew up the DNA. And within serum, we have a lifetime on the order of a day or so. We've also found that if we chemically cross-link those lysines with glutaraldehyde, we could increase the resistance against nucleases by 2 orders of magnitude. So we could have structures that can survive for weeks, even with nucleases. But there's other mechanisms to clear particles in our body. So you also have things like macrophages that will engulf the particles and then subject it to even more degradative environments. There's a lot of macrophages in the liver. It's kind of designed or evolved to clear foreign particles, digest them. So currently, I would say it's a big research challenge if your goal is to make therapeutic structures that can persist for really long times. Like one goal would be to make it last as long as a circulating red blood cell. So red blood cells can circulate for something like 4 months. And that's something that DNA nanostructures cannot do yet. But I believe that we'll get there because it's just chemistry that allows the red blood cell to last that long. So there must be some kind of solution through chemistry that will allow nanoparticles to do the same thing. Thank you.
If we put this DNA origami in our body, then how in order to be released, it should be digested by enzyme or the way this to be down origami, this can be discussed.
Right. Yeah, great question. So I think one gets especially worried about this kind of issue with some of these inorganic particles like carbon nanotubes or gold nanoparticles, because if they don't degrade and all they do is just accumulate, they're going to cause problems. So that's one of the comforting things about using some kind of material that is natural, so DNA is biodegradable, and we can tune. One important thing is we can tune to some extent the rate at which it's degraded. I just described some methods of doing it, like coating it with polymers, cross-linking. So we can decide, or maybe based on our experiments, how long do we want this to last in the body before it gets cleared, and then design the protection accordingly so that, for this application, I want it to be cleared within 24 hours. So I'll use this coating. For this other application, maybe I want it to last for a month. So maybe I'll use some more aggressive coating, or maybe I'll sequester it in some macroscopic gel that's time released. So the stuff on the inside of the gel doesn't see the light of day until it's like a Tootsie Roll, and then it shrinks and then eventually gets released. So I think that's the way to think about it. You want to be able to engineer the degradative potential of the material so it'll disappear when you want it to.
Try to make steel
Yeah, thanks. Yeah, there's been some work on those kinds of things. So Phil Holliger at MRC in University of Cambridge. So he's developed these, he calls them XNAs. So they're completely unnatural nucleotides, and he evolved polymerases that can actually polymerize them. And I was kind of amazed that they took work that I did as a postdoc to make this self-assembling octahedron, and then they just did the same thing with XNAs, and then they showed that it worked. So I think it's definitely possible to make a lot of these structures with unnatural things. And in fact, just one of the things that we all have to deal with as scientists is our scientific mortality, that at some point in time, whatever you make is going to become obsolete. Your tool will be superseded by something that's better. But the saving egotistical imagination is that, well, maybe DNA will become obsolete someday for making these objects. But I think there's a chance that some of the bigger ideas, the abstract ideas like this crisscross assembly, will survive the specific physical substrate. Because I just showed you that crisscross polymerization works for single-stranded slats, DNA origami slats. That says the idea is different than the material. So we should be able to repeat this idea with peptides or carbon nanotubes decorated with little glues, or whatever physical material of the future that has superior mechanical material properties, but we'll still face some of the same limitations. How do we grow big structures in a seed-dependent fashion? We could still use this algorithm, just don't have to use the material anymore.
Yes. One comment or question? terms of extending the acceptable lateral side to the strategy looks quite good. But to me, it seems that your assembly DNA origami is like twisted. So in order to diversify the accessible in the practical application, it would be more risk, right? So can you have?
Yeah, that's a great question. For if there's an application, I guess I would think of rigidity in two ways. So one is to make the structure more uniform, so fewer deformations from the ideal. So that's one question. And the second question could be, maybe you can accept some of these deformations, but you just want overall to have better overall mechanical properties. You want your overall structure to be more rigid. And so one attractive strategy that I could imagine is, what if we think of our DNA nanostructure as a kind of flexible skin, and we're going to apply this flexible skin over a mechanically stronger substrate. So I'm thinking like, let's say a sheet that we're stretching across a base to make a drum. And so by applying the skin by itself is very flexible. It's not very strong. But if you take the skin and then you stretch it tight across a much more rigid object, now you could argue the skin now becomes very well ordered because of the tension. And it's very strong because it's basically counterbalancing tension with the compressive forces of the base. So maybe we could wrap the skin of a DNA megastructure around a microparticle. So the microparticle will now imbue strength on the overall system. And maybe if there could be some kind of something like inflating the balloon, that by the crisscross structure, maybe under a tensile regime, now becomes very, very well defined. But versus if you don't have that tensile strength, then it's more disordered. So those are some ideas of how to do it. You could also imagine other tricks, like the fact that your crisscross sheet has, it basically has it's loose, but it has these sequence-specific glues. So what if you have a microfabricated surface? Again, your microfabricated surface is perfect. And then you land your crisscross structure on your microfabricated surface. And the only way, you're using maximizing surface energy to force your otherwise loose structure into this much more regular arrangement. So tricks like that, I think, could get you towards that goal.
Question or comment? Yes, if not, yes, thanks again for
Well, thank you very much.